Hey, what's going on, guys? Let's do this problem right here. This question is asking for the junction temperature and Q dot. Here we have 100 degrees Celsius connected to 0 degrees Celsius by a bar, and this bar contains copper 0.8 meter and aluminium 2.0 meter. Now let's see how we can calculate these values. The key idea here is whenever we have heat transfer in series, it's going to be equal everywhere. For copper, heat transfer rate and aluminum heat transfer rate is going to be equal. So that's the thing we are going to use right here. Since this is a conduction process, we are going to use this equation, that is Q dot is equivalent to Ka delta T over L, right? So this is the equation we are going to use. Now let's apply this one for copper and aluminum. Now let's begin with copper. For copper, we are going to have Kcu and ACu, delta TCu and LCu, right? So this heat transfer rate is going to be equivalent to aluminum's heat transfer rate because both are in series, so it's going to be equal. Now this is KAL, AAL, and this is going to be delta TAL over LAL, right? Now let's see how we can figure it out. So here, if you notice this length, about this length, copper length and the aluminum length, we know that aluminum is 2.0 meter, copper is 0.8 meter. Now let's make a connection. 0.8 times which value give us 2? If you think about it, 0.8 times 2 is 1.6 and 2.5 is going to give us 2 meter, right? So we can plug this one, instead of writing LAL, I can replace this one with 2.5 LCU, right? If I plug this one, I can cancel both of them. So from this one, I can cancel this LCU and this LCU. 2.5 is remaining. And also cross-sectional area for both of them is going to be equal. Cross-sectional area for copper and aluminum, since this is the same bar, is going to be equal, so we can cancel those two too. Now these are the only things that's remaining. Now let's write the new equation. This 2.5, if I bring to other side, this is going to multiply right here. So this is going to be 2.5 Kcu times delta Tcu is equivalent to Kal delta Tal, right? So let's write this one in bottom. Kal times delta Tal. Now here we have two unknowns. We know Kcu value that's provided right here, and we also know Kal, delta Tcu, delta Tl. Both of them is unknown. Now we have to write in one term to solve for one of them, right? So now let's write everything in terms of Tcu. 2.5 Kcu delta Tcu is equivalent to Kal. Instead of delta Tal, I can write 100 minus delta Tcu, because at this location the temperature is going to be equal to 100 minus delta Tcu. If you subtract that one, that's going to be the temperature right here. Temperature difference right here, right? So this is going to be 100 minus delta Tcu. Now we have all the values. Let's plug the values. So first start with this one. We have 2.5 times Kcu, that is 385, times delta Tcu, that's what we are trying to find. That is equivalent to Kal, that is 205, times 100 minus delta Tcu, right? Now let's simplify this one. 2.5 times 385. If you multiply this one, you will get 962.5 delta Tcu, and 205 times 100, that's going to be 20500 minus 205 delta Tcu. Now let's solve for Tcu, and if you bring these two to this side, this is going to be add with this one, and if you add them together, 962.5 plus 205, that's going to give you 1167.5 delta TCU. That's equivalent to 20500. And if you solve for delta TCU, you should get 17.56 degrees Celsius. Now this is delta TCU, right? But our purpose is to find junction temperature at this location. To find the temperature at this location is going to be same as aluminum's delta TAL difference. That's going to be 100 minus delta TCU. That's going to be 17.56 degrees Celsius. And if you calculate this one, you should get 82.44 degrees Celsius, right? Now this is our first question. Now let's look at the second question. Second question is asking for Q dot. So since this is in series, we know that Q dot is going to be equal everywhere. So if we solve for one of the condition, that's going to be equal everywhere. Now here we know the delta TCU, right? So because we know delta, we have to know delta T for one of them. We have available for delta TCU, so we can apply copper's information to find Q dot value. So since we don't have enough space, let's get rid of this part. Right, so let's solve this one right here. Here we are trying to find Q dot. Q dot equal this value. Now let's apply for copper. Q dot is going to be equivalent to KCU ACU delta TCU over LCU. Okay, here we need cross-sectional area, right? So let's say this area is 10 centimeters square. So that's going to be equivalent to 0.01 meter square, right? Because 10 times 10 to the power minus 4, you should get this value. Now let's plug the values. KCU is going to be 385 watts per meter Kelvin, and the area is going to be 0.001 meter square times delta TCU. We calculated right here. That's going to be 17.56. So it doesn't matter Kelvin or degree Celsius because the difference is going to be equal even if you put Kelvin. For example, if you have initial and final in degree Celsius, if you convert that one into Kelvin and subtract, you will still get the same value. So it doesn't matter whether you put Kelvin or degree Celsius. Here I put Kelvin because I want to cancel this unit right here, watts per meter Kelvin. This Kelvin and this Kelvin cancels. Finally we will end up with the right unit, right? And length of this copper is 0.8 meter. So if you notice the units, we have meter square right here. 1 meter cancels with this one, other meter cancels with this one, Kelvin cancels. Finally we will end up with watts, and this is going to give us 8.45 watts, and that's going to be our final answer. I hope you guys find this video helpful. See you next time.